All right. Good day, folks, whether it's morning or afternoon or evening. I hope you're having a good one. What we are going to do here, what I'm going to do here is a few more examples from section 6.1. Today in class we had some time to talk about like greatest common factors and factoring by grouping and all those kinds of things. And we did a few examples together, but it never hurts to have a few more, right? So I'm going to do these two examples first. I'm going to find the greatest common factor for three integers, and then I'm going to find the greatest common factor for these two kind of more complicated expressions, right? So, right, so that's the goal for each of these. It doesn't have instructions, but what we're trying to do is we're trying to find GCF. Not trying to factor anything out, we're just trying to figure out what it is. So we talked about, okay, when you have a situation like this with three integers, is you want to look for the prime factorization first, right? So we got to break down each of these numbers into their prime factorization. So let me try to do this. 105 is 5 times 21, I think. Right, so that's the first part of this factor tree for 105. Yeah, that makes sense. 5 is already a prime number, so we're good there. And then 21, of course, factors into 3 and 7. Okay, so myself a line here so I can organize my work, and I'll finish up the prime factorization for 105 over here. 105 equals 3 times 5 times 7, right? All right, what about 40? So 40 is 5 times 8, and 8 is 2 times 4, and 4 is 2 times 2. So it looks like the prime factorization for 40 is 5 times 2 times 2 times 2. 40 equals, let's see, 2 times 2 times 2 times 5. Okay, so there's my prime factorization there. And then for 60 is, well, I know it's 2 times 30. I know that 30 is 15 times 2. And I know that 15 is 3 times 5. And so that, I think, completes my factor tree. Here's my prime factors. 2 times 2 times 3 times 5. So 60 equals 2 times 2 times 3 times 5. Does that work out? 4 times 15 is 60. Yep. Excellent. Good. So we've gone through all of that process. It's a little bit like you might be sitting there thinking, oh no, like I already found the greatest common factor. I didn't have to do all this stuff with the factor trees and things. Why do we have to do all of that? Now, I guess you might be right. Like if you're really, really good and kind of perceptive and intuitive, you might be able to just look at these numbers and figure it out using a different process. What I love about this process is that it always works, right? So if you ever are in a situation where you just can't see it right away, you can't see what that GCF is right away, then knowing this process is a nice way to kind of get you to your final answer. It always works, okay? But so now that we have these prime factorizations written out, remember what we do is we look for, I'll change up the chalk. We look for common factors, right? What they all have in common. And it looks like they all have a 5 in common. So it's kind of like this. Okay, they don't all have a 7 in common. Is that it? The only thing they have in common is 5? Okay. Yeah, it looks like the only thing that they have in common is 5. And is that the right move? Yeah, that's the right move. Okay, there's a 3 here and a 3 here, but there is no 3 as a prime factor of 40, so we can't use that. And then 40 and 60 both have factors of 2, but 105 does not, so we can't include that. So the GCF for these 3 numbers, believe it or not, for all of that work, it's just 5. It's the only number, it's the biggest number that will divide into all 3 of those, okay? All right, so that's another look at finding the GCF for integers. Here's another look at finding the GCF for sort of like more complicated kind of like polynomial expressions, right? So what do we have here? We have 9m squared n and then p to the 8th. Okay, so this, you could say this kind of has 4 factors in it. It has a 9 times m squared times n to the 1st times p to the 8th. Okay, here, 15 times n to the 4th times p to the 5th. It's got 3 factors in it. And so where I'm going to start is I'm going to look at 9 and 15 and figure out what is the GCF for those. Well, 9 is 3 times 3, and 15 is 3 times 5. Okay, these factor trees are pretty, they come out pretty quick. The only factor that those two numbers have in common is the 3, and so my GCF is going to start with 3. Okay, the GCF of 9 and 15. Okay. Next, I'm on to the kind of variable parts. Okay, here I have an m to the 2nd power, but there I don't have any m's at all. There are no m's that are a factor in this expression. So there is going to be no m factor in my greatest common factor. Okay. Let's move on to n. I do have an n factor here to the 1st power, and here I have an n to the 4th, which means the greatest common factor for the n's is just going to be n to the 1st. Okay, this n and then one of those. And then the last bit, I have my p factors. This is p to the 5th and that's p to the 8th. So between the two of those, I can pull out a p to the 5th. It's getting a little messy here, so I'll rewrite it. I'll actually rewrite it over here. So my GCF, as I said, is going to be 3 n to the 1st, and then the last factor here is going to be p to the 5th. I can factor out, you know, p times p times p times p times p here, and then the same there, but that's all. I can't do any more because I run out of p's over there if I do more than 5. Okay, so that's finding the GCF for kind of a polynomial expression. In the next video, I will talk a little bit about factoring out binomials, and we'll do some examples with factoring by grouping. So that is coming up next. I'll see you there. Cheers.